This week, we get to look at circles. Circles, you gotta love them. This week, we will start with some of the basics and then see how they can apply for very advanced SAT math questions. Let's start with some vocabulary review. First off, radius. Radius is the defining characteristic of a circle, and it is the distance from the center to the edge of the circle. In this diagram here, we've drawn in a couple of radii, and note each of which has the same length. That is very important for our radius, which is that wherever you draw it, as long as it goes from the center to the edge, it has the same length. The diameter is the longest distance across the circle and is simply twice the radius, as we see again in the diagram. Now the circumference is the length around the edge of the circle and is directly related to the diameter by pi, so c equals pi d. Or more simply, using the radius, as you probably recognize, c is equal to 2 pi r. If something is tangent to a circle, that means it touches the circle only at one point. So don't confuse that with the trigonometric function tangent. Now, knowing all of this vocabulary, let's apply this to a challenging SAT example. In the figure below, the smaller circles have a radius of 3. These smaller circles are tangent to the big circle at A and C and tangent to each other at B, which is the center of the larger circle. What is the perimeter of the shaded area? If you thought at the beginning of this video that circle problems would be easy, hopefully this example shows you that that is not the case. Our later examples will only get harder, so let's go ahead and get started with this one. We are looking for the perimeter of this section here. What do we know? Well, we are given that the radii of the two smaller circles are each 3, so we can draw that in. Now, what does that give us? Well, we see that part of the path runs along the circumferences of both circles. Now, just looking at the picture, if we take that green line folded over on itself, that would just equal one circumference of these small circles. Really, it's 2 halves of both. So we can find that that distance is equal to the circumference of these smaller circles. How do we find the circumference? Remember, it's 2 pi r. The radius we're given is 3, so simply calculating, we get that that distance x is 6 pi. Great, so we have half of our path length. Now the other half, y, going along the top of the big circle. Again, just looking at our diagram, we can see that this distance is 1/2 of the circumference of the big circle. So let's find the circumference of the big circle. Again, it's 2 pi r, but this time we don't know the radius of the big circle, but we can find it. Let's look at our diagram, and we can see that the radius of the big circle is the diameter of the small circle, which is just 6, as we again see in our diagram. Plugging that in gives us that the distance y is equal to 6 pi. So our final answer is the sum of x and y, which is 12 pi. Problems using arcs and sectors can make our life even harder for SAT circle problems, so let's do an example together. Pip ties his dog's 20-foot leash to the corner of a long fence and a barn which extends 15 feet perpendicularly to the fence and extends 30 feet along the fence. What is the area that Pip's dog can walk while on the leash? For a problem like this, we'd probably be given a diagram like we see here. Let's start by identifying the area that we're being asked to calculate. First off, the dog can walk from the edge of the fence to the edge of the barn, but it can also walk around the corner of the barn in this small yellow area that we see here. So we can find our area by breaking it down into these two segments. First off, the blue area, the big one on the left. Now, the area of a sector we saw before is theta over 360. Theta here is 90 degrees, which we see because the barn and the fence are perpendicular. So we plug that in, and then we plug in the radius, which is the length of the leash, 20 feet, and we find that area is equal to 100 pi, going step by step. Next up, we want to find the yellow area. That, likewise, is theta over 360 times pi r squared. Again, we see that theta is 90 degrees, so we're going to have a quarter of a circle. But then here, what is the radius? Well, the radius is the length of the leash, 20, but then minus the distance the dog has to walk to get to the edge of the barn, 15. So our radius for this small area is 5. Plugging that in, we get that the area of this smaller segment is equal to 25 pi over 4, much smaller than the blue area as we would expect. So plugging that in, we find that the area combined is just the total sum of these two numbers, which is 106.25 times pi. Next up, we're going to look at equations of circles. The general equation for a circle centered at the origin with radius r is, as we see here, x squared plus y squared equals r squared. We can understand where this comes from by looking at a circle in the coordinate plane. Recall that a circle is defined by the set of points that are all the same distance to the center of the circle. So that means if we look at this point on the circle x comma y, then those have to have distance to the center equal to the radius, r. That is the definition of a point on the circle. How do we state that mathematically? Well, to calculate distance in a coordinate plane, you use the Pythagorean theorem. The distance is the square root of x squared plus y squared. And as we said, that has to equal r. So if we simply square both sides, we're going to get the equation that x squared plus y squared equals r squared. Now we derive this just by saying that any point has to be the same radius away, but we see we get the same equation we just saw for the equation of a circle. Now if we see the following problem, we can quickly answer it. Given this equation of a circle, what is the radius? Comparing this equation with the general form, we can see that the number 81 plays the role of r squared. So 81 is equal to the radius squared, which means to find the radius, we just square root both sides, and we find that the radius is equal to 9. And it's as simple as that. Now for the last layer. What about a circle centered not at the radius, but at the point a comma b? This would look like x minus a squared plus y minus b squared equals r squared, as we see here. So where did this minus a and minus b come from? Well, you can think of them as shifts, like we saw in our transformations video, which I suggest you watch again here. It's an x shift and a y shift, just like we saw there. Now you might be confused, why is the y shift looking like it's an x transformation? Well, in this case, y also acts as an independent variable like x does, so it acts the same way as x. Now for our last example. Given this equation for a circle, where is the center of that circle? Knowing what we just learned about the general equation for a circle, this is really simple. Comparing with the general form of a circle equation, we see that a equals 10 and b equals 14. Remember, a and b represent the coordinates of the center of the circle, so we can really simply say that the center of this circle is a comma b equals 10 comma 14, our final answer. And that's it for circles. You need to know how to apply radius, diameter, circumference, and not get caught off guard by arcs and sectors. Lastly, as we just saw, you need to know how to recognize and understand equations of circles. Circles don't show up that frequently on the SAT, but I promise you, these can be some of the most tricky problems, so I strongly recommend you get some good practice with it. Hope you liked the video. If you want to hear more and see what else we're up to, hit like and subscribe, and see a new video coming out from Point Avenue every week. If you want to talk to us, hear more about what we're doing, or have any questions, email us at contact@pointavenue.com. Bye!